Yes, under certain conditions, a grounding electrode can serve as a neutral conductor through the ground. When a neutral line is lost, the grounding electrode can provide a path for the return current, potentially preventing dangerous overvoltages on 120-volt circuits. Firstly, the resistance of the grounding system is a key factor. The grounding electrode must have a low enough resistance to allow current to flow through it. Typically, a resistance of less than 25 ohms is considered acceptable. Secondly, the availability of multiple grounding paths matters. In addition to the grounding electrode, other paths to ground may exist, such as metal water pipes or structural steel. These paths can also contribute to reducing the resistance and providing a reliable neutral return. Thirdly, circuit topology matters. The wiring configuration of the electrical system can affect the effectiveness of the grounding electrode as a neutral return path. In some cases, the grounding electrode may not be connected to the neutral bus in a manner that allows it to function as a return path. However, it's important to note that relying on the grounding electrode as the sole neutral return path can be risky. High resistance is a factor. If the grounding electrode has a high resistance, it may not be able to handle the full return current, resulting in voltage fluctuations and potential damage to equipment. Lack of redundancy is also a concern. If the grounding electrode is the only neutral return path, a loss of contact or damage to the electrode can leave the electrical system unprotected. Therefore, it's recommended to ensure that the electrical system has a properly sized and dedicated neutral conductor. The neutral conductor should be connected to the neutral bus and provide a low resistance path for the return current. Using the grounding electrode as a supplemental neutral return path can provide some level of protection, but it should not be relied upon as the primary neutral return path. Let's delve deeper into the role of grounding electrodes and neutral conductors in electrical systems, focusing on how they interact and the potential consequences of a lost neutral. The grounding electrode's primary function is to provide a low impedance path to ground for fault currents. This helps to quickly trip circuit breakers or fuses, protecting equipment and people from electrical shock hazards. The grounding electrode is typically a metal rod, pipe, or plate buried in the earth, and it's connected to the electrical system's grounding bus. The neutral conductor, on the other hand, is the return path for normal load current. It's typically a white or grey wire and is connected to the neutral bus in the electrical panel. In a properly functioning electrical system, the neutral conductor carries the unbalanced current back to the source, which is usually the transformer. When a neutral conductor is lost or broken, the normal return path for current is interrupted. This can cause a variety of problems, including voltage imbalances, overvoltages, and equipment damage. In such a scenario, the grounding electrode can potentially serve as a supplemental return path, but its effectiveness depends on several factors. One crucial factor is the resistance of the grounding system. A low resistance grounding system will allow more current to flow through the ground, reducing the voltage rise in the electrical system. The National Electrical Code, NEC, typically requires a grounding resistance of 25 ohms or less for a single grounding electrode. If the resistance is higher than 25 ohms, an additional grounding electrode may be required. Multiple grounding paths can also improve the effectiveness of the grounding electrode as a neutral return. These paths can include metal water pipes, structural steel, and other grounded metal objects. The more paths available, the lower the overall resistance to ground, and the more effectively the grounding system can carry fault current or, in this case, act as a supplemental neutral return. The wiring configuration of the electrical system also plays a role. In some cases, the grounding electrode may not be directly connected to the neutral bus in a way that allows it to function effectively as a neutral return. For example, if the grounding electrode is only connected to the equipment grounding conductors, it may not provide a low impedance path for neutral current. It's important to understand that relying on the grounding electrode as the primary neutral return path is not a safe or reliable practice. Grounding electrodes are designed to handle fault currents, not continuous neutral current. If the grounding electrode is forced to carry a significant amount of neutral current, it can overheat and potentially fail. Furthermore, A high-resistance grounding system can lead to voltage fluctuations and equipment damage. For example, if the grounding electrode has a resistance of 100 ohms and the neutral current is 10 amps, the voltage rise in the grounding system will be 1000 volts. This voltage can damage sensitive electronic equipment and pose a shock hazard. Therefore, it's essential to ensure that the electrical system has a properly sized and dedicated neutral conductor. The neutral conductor should be sized according to the NEC and should be connected to the neutral bus in the electrical panel. It should also be protected by overcurrent devices, such as circuit breakers or fuses. In summary, while a grounding electrode can potentially serve as a supplemental neutral return path in the event of a lost neutral, it should not be relied upon as the primary means of providing a return path for neutral current. A properly sized and dedicated neutral conductor is essential for safe and reliable operation of the electrical system. It's also important to ensure that the grounding system is properly installed and maintained, with a low resistance to ground and multiple grounding paths. Now, let's explore some specific scenarios and considerations related to this topic. In a residential setting, a typical service entrance includes a neutral conductor, 2 hot conductors, and a grounding electrode. The neutral conductor is connected to the neutral bus in the electrical panel, and the grounding electrode is connected to the grounding bus. The equipment grounding conductors from all the branch circuits are also connected to the grounding bus. If the neutral conductor from the utility transformer to the house is broken or disconnected, the 120-volt circuits in the house can experience voltage imbalances. Some circuits may see voltages higher than 120 volts, while others may see voltages lower than 120 volts. This is because the loads in the house are connected in series through the grounding system. The grounding electrode, in this case, may provide a path for the unbalanced current, but its effectiveness will depend on the factors discussed earlier, such as the resistance of the grounding system and the availability of multiple grounding paths. In a commercial or industrial setting, the electrical systems are typically more complex, with multiple panels, transformers, and grounding electrodes. The principles, however, remain the same. A lost neutral can cause voltage imbalances and equipment damage, and the grounding system may provide a supplemental return path. In these settings, it's even more important to have a properly sized and dedicated neutral conductor, as the loads are typically larger and more sensitive to voltage fluctuations. Another important consideration is the type of grounding system used. The NEC recognizes several types of grounding systems, including grounded, ungrounded, and impedance-grounded systems. The type of grounding system can affect the behavior of the electrical system in the event of a lost neutral. For example, in an ungrounded system, there is no intentional connection between the electrical system and ground. In this case, a lost neutral may not cause immediate problems, but it can create a floating ground potential, which can be dangerous. In an impedance-grounded system, a resistor or inductor is connected between the neutral point of the transformer and ground. This limits the ground fault current and can reduce the voltage rise in the grounding system in the event of a lost neutral. In conclusion, understanding the interaction between grounding electrodes and neutral conductors is crucial for ensuring the safety and reliability of electrical systems. While a grounding electrode can potentially serve as a supplemental neutral return path in the event of a lost neutral, it should not be relied upon as the primary means of providing a return path for neutral current. A properly sized and dedicated neutral conductor, along with a properly installed and maintained grounding system, are essential for protecting equipment and people from electrical hazards. Always consult with a qualified electrician or electrical engineer for specific recommendations and guidance on electrical system design and installation. Let's further elaborate on the practical implications and considerations for maintaining a safe and reliable electrical system, particularly in the context of a lost neutral scenario. One critical aspect is regular inspection and testing of the grounding system. Over time, grounding electrodes can corrode or become damaged, increasing their resistance to ground. It's recommended to periodically measure the grounding resistance using a ground resistance tester. This test involves injecting a current into the ground and measuring the voltage drop to determine the resistance. If the resistance is higher than the recommended value, the grounding electrode should be repaired or replaced. Another important practice is to ensure that all grounding connections are tight and corrosion-free. Loose or corroded connections can significantly increase the resistance of the grounding system, reducing its effectiveness. All grounding connections should be cleaned and tightened regularly, and corrosion-resistant material should be used. In addition to the grounding electrode, all other grounding paths, such as metal water pipes and structural steel, should be inspected and maintained. These paths can provide valuable supplemental grounding, but they must be in good condition to be effective. Another aspect to consider is the impact of harmonics on the neutral conductor. Harmonics are non-sinusoidal currents and voltages that can be generated by electronic devices such as computers, variable frequency drives, and LED lighting. Harmonics can cause the neutral current to be significantly higher than the phase currents, which can overload the neutral conductor and potentially lead to lost neutral. SPD are designed to divert surge currents to ground, preventing them from damaging equipment. SPD should be installed at the service entrance and at branch circuits that serve sensitive equipment. In the event of a suspected lost neutral, it's important to take immediate action to prevent damage to equipment and ensure safety. The first step is to disconnect all non-essential loads. This will reduce the amount of current flowing through the grounding system and minimize the voltage rise. The next step is to check the voltage of various outlets and equipment. If the voltage is significantly higher or lower than normal, it's a sign of a lost neutral. A qualified electrician should be called to investigate the problem and make the necessary repairs. It's also important to document the incident and any damage that occurred. This information can be used to prevent future occurrences and to support insurance claims. In addition to these practical considerations, it's important to stay up to date on the latest codes and standards related to electrical safety. The NEC is updated every 3 years, and it contains the latest requirements for electrical installations. It's also important to participate in continuing education and training programs to stay informed about new technologies and best practices. By following these guidelines and taking a proactive approach to electrical safety, it's possible to minimize the risk of a lost neutral and ensure the safe and reliable operation of electrical systems. Now let's delve into specific code references and calculations relevant to grounding and neutral conductors. The National Electrical Code, NEC, provides detailed requirements for grounding and bonding of electrical systems. Article 250 of the NEC covers grounding and bonding, and it includes specific requirements for grounding electrodes, grounding conductors, and bonding jumpers. Section 250.50 of the NEC requires that all grounding electrodes be bonded together to form a grounding electrode system. This ensures that all parts of the grounding system are at the same potential. Section 250.52 specifies the types of grounding electrodes that are permitted, including metal water pipes, metal frame of the building, concrete encased electrodes, and ground rings. Section 250.66 provides requirements for the size of the grounding electrode conductor. The size of the grounding electrode conductor is based on the size of the service entrance conductors. Section 250.102 provides requirements for bonding jumpers. Bonding jumpers are used to connect different parts of the electrical system together, such as metal conduits, metal enclosures, and equipment grounding conductors. Section 300.3b requires that all conductors of a circuit, including the neutral conductor, be installed together in the same raceway or cable. This minimizes the impedance of the circuit and reduces the voltage drop. Section 310.15 provides requirements for the ampacity of conductors. The ampacity of a conductor is the maximum current that it can carry continuously without overheating. The ampacity of a conductor is based on its size, insulation type, and the ambient temperature. When calculating the neutral load for a service or feeder, it's important to consider the unbalanced load and any harmonic currents. The unbalanced load is the difference between the current on the phase conductors and the neutral conductor. If there are significant harmonic currents, the neutral load may be higher than the unbalanced load. The NEC provides guidance on calculating the neutral load for harmonic currents. In some cases, it may be necessary to oversize the neutral conductor to accommodate the harmonic current. Excessive voltage drop can cause equipment to malfunction or not operate properly. The NEC recommends that the voltage drop in a branch circuit not exceed 3% and the voltage drop in a feeder not exceed 5%. The voltage drop can be calculated using Ohm's law V equals I times R, where volts is the voltage drop, I is the current, and R is the resistance of the conductor. By understanding these code references and calculations, it's possible to design and install electrical systems that are safe, reliable, and compliant with the NEC. Now let's consider the role of isolation transformers and their potential application in mitigating the effects of a lost neutral. An isolation transformer is a transformer with separate primary and secondary windings that are electrically isolated from each other. Isolation transformers are often used to provide a clean, stable power supply to sensitive electronic equipment. They can also be used to isolate equipment from ground loops and other electrical noise. In the context of a lost neutral, an isolation transformer can provide a degree of protection by isolating the equipment from the voltage fluctuations and imbalances that can occur. If the neutral is lost on the primary side of the transformer, the secondary side will still maintain a relatively stable voltage. However, it's important to note that an isolation transformer does not completely eliminate the risk of damage from a lost neutral. Another approach to mitigating the effects of a lost neutral is to use a constant voltage transformer, CVT, also known as a ferroresonant transformer. A CVT is a type of transformer that is designed to maintain a constant output voltage even when the input voltage varies. CVT can provide a high degree of voltage regulation and can protect equipment from voltage surges and sags. In the event of a lost neutral, a CVT can help to maintain a stable voltage on the load side, preventing damage to equipment. However, CVT are also expensive and inefficient, and they may not be suitable for all applications. In some cases, it may be necessary to install a dedicated neutral conductor from the utility transformer to the building. This provides a redundant neutral path and can reduce the risk of a lost neutral. The dedicated neutral conductor should be sized according to the NEC and should be connected to the neutral bus in the electrical panel. Another approach is to use a three-phase power system instead of a single-phase system. In a three-phase system, the neutral current is typically much lower than in a single-phase system. This reduces the risk of overloading the neutral conductor and can make the system less susceptible to a lost neutral. However, three-phase power systems are more complex and expensive than single-phase systems, and they may not be practical for all applications. In conclusion, there are several approaches to mitigating the effects of a lost neutral, including using isolation transformers, CVTs, dedicated neutral conductors, and three-phase power systems. The best approach will depend on the specific application and the level of protection required. It's important to consult with a qualified electrician or electrical engineer to determine the most appropriate solution. Let's further discuss the diagnostic procedures and troubleshooting steps that can be taken when a lost neutral is suspected in an electrical system. The first step in troubleshooting a lost neutral is to gather information about the symptoms and the circumstances surrounding the problem. Some common symptoms of a lost neutral include flickering lights, dimming lights, appliances not working properly, and unusual voltage readings at outlets. It's important to ask questions such as when did the problem start? What appliances are affected? Have there been any recent electrical work or storms in the area? Once the symptoms have been identified, the next step is to perform a visual inspection of the electrical system. Look for any signs of damage or loose connections at the service entrance, electrical panel, and outlets. Check the neutral conductor for any signs of burning or corrosion. Use a voltmeter to measure the voltage of various outlets and equipment. In a properly functioning 120-volt circuit, the voltage should be close to 120 volts. If the voltage is significantly higher or lower than 120 volts, it's a sign of a lost neutral. It's also important to measure the voltage between the neutral conductor and ground. In a properly functioning system, the voltage between neutral and ground should be close to 0 volts. If the voltage between neutral and ground is higher than 2 volts, it's a sign of a problem. Use an ammeter to measure the current on the neutral conductor. In a properly functioning system, the neutral current should be relatively low, especially in a balanced three-phase system. If the neutral current is unusually high, it's a sign of a problem. If a lost neutral is suspected, the next step is to isolate the problem. This can be done by turning off circuit breakers one at a time and observing the voltage readings. If the voltage returns to normal when a particular circuit breaker is turned off, it indicates that the problem is on that circuit. Once the problem has been isolated to a specific circuit, the next step is to inspect the wiring and connections on that circuit. Look for any signs of damage or loose connections. Check the neutral connections at the outlets, switches, and light fixtures. If a loose connection is found, tighten it securely. If a damaged wire is found, replace it with a new wire of the same size and type. If the problem cannot be found by visual inspection, it may be necessary to use a wire tracer to trace the wiring and identify any breaks or shorts. A wire tracer consists of a transmitter and a receiver. The transmitter is connected to the wire to be traced, and the receiver is used to follow the signal on the wire. Once the problem has been identified and repaired, it's important to test the system to ensure that it is working properly. Use a voltmeter to measure the voltage of various outlets and equipment. Use an ammeter to measure the current on the neutral conductor. Verify that the voltage between neutral and ground is close to 0 volts. Finally, it's important to document the problem, the troubleshooting steps, and the repairs that were made. This information can be used to prevent future occurrences and to support insurance claims. In conclusion, troubleshooting a lost neutral requires a systematic approach that includes gathering information, performing a visual inspection, taking voltage and current measurements, isolating the problem, and testing the system. By following these steps, it's possible to identify and repair a lost neutral and ensure the safe and reliable operation of the electrical system.